Hello and welcome to this session at Blockchain Week. Today we have speaking with us Peter Robinson, and he's a blockchain researcher from ConsenSys, and he'll be speaking about DeFi Bridges. Over to you, Peter.
Thank you. Thank you. And hello, everyone. So DeFi Bridges, what is a bridge? What is it all about? So today, most bridges are all about asset transfer. You've got an ERC20 token or some Ether on one chain, and you want to move it to a different chain. You want to get that asset transfer to go across chain. And, so you can be doing that, but also you could be doing business logic across chain. So you can think of at the moment, you might have, say, two smart contracts on the same blockchain. What about if they were on different blockchains? What about if you have, say, some liquidity on one chain and you have some ERC721 NFTs on another chain, and you need some logic around them, and you want to be able to do some business transactions across those chains? So that's what bridges are about, and that's the two types really. You've got these asset transfer and business logic ones. So ones where you can spread your business logic around. So why would you use a bridge? Why don't we all just use Ethereum mainnet? Well, obviously transaction fees come in there as a big one. And so some chains, the transactions cost more than others. There's also functionality. If some token drop's being done on a certain chain, you need to be doing the stuff on that chain. So you need to move to that chain. But also there might be some functionality, for instance, some automatic market maker that you want to participate in on some other chain. So that functionality drives a lot of why you use a certain chain as well. You also might do it because of liquidity pooling. So maybe you're going to have a larger liquidity pool on one chain, and if you move all your liquidity together, then it makes it easier to trade. Or there could also be capital utilization and efficiency, which is again able to utilize all your assets on one chain. But if you could do that cross-chain business logic, though, maybe you could tap into your assets across chains. There's also security and decentralization reasons. So you might be prepared to use a chain that's got, say, more centralization and less security temporarily to do something and then quickly exit it. So trying to limit your window of potential failure. So when we think about these cross-chain bridges, you've got on the source side, you're going to have, say, an ERC20 contract, and I think of them as mass conservation. So you can't create new matter and you can't destroy it. And so in this case, you can't just randomly create new ERC20s or destroy them. And you have a bridge across to another ERC20 on a different blockchain. And you can think you've got there what's called a minter-burner contract, where when you transfer tokens across, so it gets owned by the bridge on the source, and on the target, you mint some new tokens. And then when you want to go in the opposite direction, you then burn those tokens on the target, and then they end up on the source again, and you have them there. So if there are a dozen bridges rather, going to the same chain, and they've all got their minter-burner ERC20 contract, then, are those all the same? Well, they're not. And so you might, even if they're all wrapped ETH or wrapped some other token, at the end of the day, they're all in parallel. And when you want to do some token, participate in some token drop or something like that, you're going to be needing to use a specific token. And what's likely to happen on these chains is that people are going to sort of gel around, hey, I always want to use that version of the wrapped ETH. And so you can imagine that could be called the canonical ERC20. And so now you've got these other ERC20s that are wrapped, they're wrapped for the same asset, and you've got the canonical one. So you typically will use an automatic market maker to switch between those two tokens, and to try and go from, say, your source chain to your target chain, and then get to the actual ERC20 that you actually need. So that overall scheme is how things happen. And so when you try and think about, all right, so based on that sort of like loose understanding of how these bridges work usually, well, what attacks have happened? And, because if you think of attacks, then it helps to inform you about, how things can work and how things can go wrong. And a really big attack was the Poly network attack. And it was where $600 million was essentially stolen. Due to all sorts of circumstances, a whole heap of it got given back. But there's a few things to think about here. One is $600 million got stolen. That means there's $600 million was on that bridge. And so that's a lot of money. So the reason why the hack happened was there was a bug in the code, which really came down to poor access control and poor separation of roles and responsibilities within the contract code. And so then there was the Solana hack, the wormhole bridge. And again, this one was a bug in the code. And so the bigger thing though was the poor vulnerability response. So what happened was there was some code that got written that then someone noticed there was a bug. They fixed the bug and they did a pull request sent to the public repository. 2 weeks go by. Obviously, a hacker notices, hey, there's been a bug. The bug fix hasn't been deployed. They exploit, and then a bit later, the fix gets deployed. So, that's really poor vulnerability response. The code was public, and that's good though, because that means that you've got more eyes on the code. But in this case, the bug was in Solana code. And so most people who know, say, Solidity and Ethereum virtual machine environment stuff, they don't know Solana. So if the bridge includes a computer language or an environment that people aren't used to or accustomed to, then it's hard to review. So you're increasing your probability of bad things happen. But certainly the poor vulnerability response that they had was pretty awful too. A third one that I'd like to talk about is the Cello Optics bridge. So when they were in beta, they had an employee who had actually helped lead up the development. And for reasons that aren't public, that person was fired. So it's not a technical reason. And the CEO put a blog post up, which he probably said things that, I don't think his HR would have advised him to say. But anyway, so he pretty much accused the person of being the source of the attack. And so anyway, the 15 minutes after that person was fired, they put the whole bridge system into recovery mode. And so the thing was that to go into recovery mode, a certain account had to trigger it. And that should have been a multi-sig wallet. But in fact, it was only an externally owned account, so only a single private key, public key pair. And there's also was supposed to be a time lock of 1 day. And so the idea is that someone put it into recovery mode and then everyone would say, oh, I don't agree with that. And they'd have time to exit. So instead of 1 day, it was 1 second. So essentially, as soon as it was done, boom, it's happened. And so what that shows is a lack of of control of the system, not the right DevOps to know, well, and auditing of have we actually got the config right? Is who actually is this account, and is it this multi-sig wallet that it's supposed to be? And so, we've got these 3 attacks here, and a lot of them are around maturity of the system and maturity of processes and maturity of the code, and also auditing and review of the code. So lots of problems in bridges. And so then I guess the question comes, so, there are a lot of bridges out there. There are dozens, if not hundreds of bridges. And so which one is the one you should use? So obviously the first option that most people go for is the cheapest one, because, cheapest one's probably going to work. Another way that people go with is, well, this person I know, my co-worker's second cousin, they used it and, it worked for them. And so, a lot of it is just referential. And another way that people it is, I guess, self-referencing. So you've got $1 million to transfer. So what you do is you transfer $100. Does that work? All right, that worked. What about 10,000? What about $1 million? And so you incrementally do it until you sort of acquire a bit of trust in the system. But I guess just because it can transfer $100, is $1 million a bigger target? And could that be then compromised? So when you're thinking about bridges, and actually if you're thinking about bridging solutions, what you should be thinking about is, well, who's being trusted? A lot of bridges claim to be trustless, but trustless is such an overused term. And it's easy to say something's trustless, but is it? Who is being trusted? And invariably there's something or some group of parties that are being trusted. And so understanding what the trust properties are, as much as anything else, it shows that the people who've made the bridge have thought about it. Is the transfer going to depend on a centralized party? So we're all into blockchain because it's decentralized. And now if suddenly the bridge requires one central party, then, is that still going to be decentralized? Is it any good? And I mean, maybe it is good. Like, I mean, if you say trust, I don't know, MasterCard with your credit card and all that sort of stuff, maybe you would trust them to be a centralized party. So it depends on who that centralized party is and what you feel about them. Atomicity is another really overused term. And so atomicity, the idea is that, if the transfer goes through on the source, then it's going to go through on the target. If it fails on the target, it'll fail on the source. So if a transfer happens on the source, and then a transfer happens on the target, and then you've got this centralized party that's there watching everything with this godlike view, and it says, oh, it's failed on the target, let's do a refund on the source. Is that atomic? Is that really atomic? And for me, not really. Atomicity has to be at the protocol level. So it's got to be baked in so that you don't need a central party who can do this. Oh, look, something bad's happened, let's reverse. You need the protocol to understand what's happening and to reverse automatically. And so having protocol level atomicity, I think, is really important. Another thing to think through when you're about to use a bridge is you're trying to move some value to the target chain, but some of the bridges rely on you being able to pay for gas on the target chain. This is obviously a problem because if you can't pay for gas, then you're not going to be able to complete the transfer, so it's not going to work. So do you need to have gas on the target? And so if you're not going to submit a transaction on the target, who is submitting that transaction? Because someone's got to submit a transaction on that target blockchain because you're giving some value on the source and you're getting some on the target. So there must be a transaction on that target blockchain. But if you're not paying for gas, then someone is. So who is it? And how are they incentivized? Why are they incentivized to do the right thing in all circumstances? And if they're not, then it might work for $100, but it might not work for $1 million. So, think very carefully about what's the incentivization structure. And if there are relayers and testers or some other components involved that vouch for things being valid and true, how are they being incentivized? How are they compensated? Are they going to be compensated such that for the scale of transfer you're doing, they're going to be good to go? And how many components in the system need to be compromised or bribed for the whole thing to fall over? And as I said before, open source code is really good because then you and other people can review it. And so then you're more likely to have people say, hey, I think this is a problem. Whereas if it's closed source, you might have a bug that's lurking there that will be found at some point, but it might be harder for other people, good people, to explain what the bug is and try and fix it. How long has the bridge been up and running? So if I deploy a bridge sometime tomorrow, then I don't think it should be as trustworthy as a bridge that's been available for a long time, because chances are, that it's been tested out. People have tried to hack it because if you deploy a bridge, people are gonna try and hack it. So if it survived all those hacks, then it's probably not too bad. Has the system been reviewed? So ConsenSys has a company that reviews a part of our business unit, should I say, that reviews code and applications. I know the Open Zeppelin project have a group that do that too. I'm sure there are many groups around the world that review applications, so the source code on chain and the off-chain components, to confirm that the overall system looks good. So what about the vulnerability response processes? So are they written up? Can you see, well, if a vulnerability does happen, is it just going to be chaos and it's going to be some Twitter argument, or is there something better? And I think if you look at some of the hacks that have happened recently, a lot of it plays out on Twitter, which is great if you want to do a talk on the hack, but not so good if you're a user. And so is there a vulnerability reporting and bug bounty system? So I've talked about other systems, but I'm a blockchain researcher and cross-chain DeFi bridge researcher, and also part of the Enterprise Ethereum Alliance's cross-chain interoperability working group. And we've been working on some cool stuff too. And well, it's a cluster of companies, organizations, and it's just, so this is we've been looking at the security of bridges and the guidelines for operating them, and just generally what should people do to try and make sure they're running something good. And one of the ideas that we've had is this thing called the Crosschain protocol stack. And so with the Crosschain protocol stack, you've got an application layer. So they're, say, DeFi applications or supply chain applications that are operating across blockchains. So you've got some business logic on this chain, business logic on that chain, and that chain, and that chain, and that roll up, and just to spread across chains. You've got a function call layer. And so this allows you to, say, have some Solidity code that's on one chain, call to Solidity code that's on a different chain, and have an arbitrary call execution tree where you've got just code calling other code, calling other code. So allowing you to compartmentalize your code, similar to how you do it in a current system where it's all on one chain, but spreading it across chains. The messaging layer allows information to be proven from one chain to another. And so the techniques needed are different for different chains and for different consensus algorithms and different properties. So some of them might be privacy centric, some of them might be permissioned or permissionless. And so all the different requirements end up meaning you have different messaging layer requirements. And so the messaging layer ensures that you have information that the function call layer can use to provide these cross-chain function calls. And the function call layer is providing capability for the application layer to call functions across blockchains. So that's, the layered architecture. And the reason for doing it is interoperability. So you can imagine you've got an application and it wants to use a function call implementation. So if we've got this standardized protocol stack, then you just need to program to an API, and then you'll be able to mix and match using the different function call protocols with their different capabilities and limitations to implement your system. It also allows for flexibility. So you can imagine you've got these different messaging systems, and so, from, say, a roll up to mainnet, you might use one thing, but then in the opposite direction, you might use a different message verification system. Also from a private chain, you might use something different. And so it allows you to mix and match. And probably, one of the big things is it's going to allow you to focus on what you're good at. And so you can imagine if you're an application company, the idea of you developing a function call protocol or a messaging system and standing that infrastructure up should be pretty frightening. And if it isn't frightening, I don't know, chat to someone about it and they'll tell you it's frightening. I can assure you that running your own cross-chain system is a fraught adventure. And there are so many hacks of people who've just tried to do a home-baked solution. It's pretty scary. So you could also imagine that there could be an infrastructure provider and they could do messaging stuff between this chain and that chain, or between a whole set of chains. And so you could use that infrastructure provider to do cross-chain messaging. And then you could say, all right, well, these people have got a great function call protocol. We'll use that function call protocol with those messaging systems to create our overall application. And so the incentivization for the lower layers is set up correctly because of how you're using the overall protocol stack. And the other thing to think about is you've got infrastructure reuse. So rather than your company setting up all this infrastructure, you might have an infrastructure provider and then multiple applications from your company, and multiple companies could be using the same cross-chain messaging layer infrastructure and function call infrastructure. So rather than you having to do all that heavy lifting, you do what you're good at the application layer. And another advantage of this system is we often hear about the idea of experimentation, but there are a lot of, I've worked with lots of students, in university students who are looking to build blockchain stuff and cross-chain stuff. And invariably they go and build the whole protocol stack. And wouldn't it be great again if they could focus on just trying out something new in a certain area? And so maybe they can then use the overall stack of technologies and just focus on that. Because, like if we think back to, say, TCP/IP and the internet and the World Wide Web, you wouldn't want to be trying to do all those layers of the protocol stack. Wouldn't it be good to just focus on one layer? And that's what people do. And so I think doing this for the cross-chain bridges and DeFi bridges will really help us move forward. Just a second. So, in conclusion, having a think about it, what do you really want to do? When you're looking at a bridge, what do you need to be thinking about? So think through who's being trusted and what trust assumptions are being made. And, is there being a centralized party, or is it decentralized? Is it really trustless? If people are saying it's atomic, how is the atomicity actually provided? And, are you sure that that's going to work given your scenario? And the other things to think about is what are the crypto economics? Who's being compensated to do what? Can they be bribed? Though it might work at, say, $100, will it work at $10,000, $100,000, $1 million, $10 million, $100 million? And I know you're saying 100 million, but people do transfer huge amounts of money around the blockchain ecosystem. So any system you create, assume someone's going to transfer $1 billion and try and think about how to make sure nothing goes bang when they do. And what systems are in place for these companies? And I know this is just normal IT that you would have for any product that you're using, but what are the systems they've got? Is this mature enough? Do they, what's their vulnerability response? How quick, when they say they release, are able to release a new version of their software tomorrow, what does that mean? Is everything automated? Do they have manual tests that they don't run each release? How does it work? And so I think that's very important. And I think I've talked enough on bridges. So have a great day, everyone, and great rest of Blockchain Week. Talk to you all later. Bye-bye.